So with this version here, 2016, some slides I changed them already. 2016, some slides I found them to be the same, so I didn't bother to change them. So I just kept them. And from time to time, you're gonna see AISC and then 341, 05, or 10. This is fine, just use them as is. We're gonna stay with whatever that we have in the slides. So if there's any discrepancy or any difference, please use the one that you have in the slide. Eric, too, all right. Eric, are you in? Eric? Mr. Eric?
Hello, Professor. Sorry I was late.
Yeah, that's fine. Okay, so Eric is here. So still have Marlene, and she's not coming today, so we should be fine. Okay, so in this size provisions, in this seismic code, if you like to call it seismic code for structural steel buildings, we have all of the chapters. The two chapters I care about because they have general information and general kind of requirements that you need to be aware of is give you chapter A and B. When it comes to analysis, not really critical because we're going to be addressing the analysis. There's nothing here new for you to understand or to know about. After this, we're going to have general member and connection design requirements. This is true, but most importantly, that we're going to have this moon frame system. And this is the one that includes special size of moon frame and ordinary and intermediate. And also we have this brace frame and shear wall systems given in chapter F. Here is what you have in chapter B that I'd like to stress on, general design requirements. Now, when it comes here to the general design provisions, of course, you're going to be using the CBC and ASCE. So this is exactly what it says. So you need to follow CBC and ASCE. When it comes to design forces, when it comes to design requirements, when it comes to allowable drift. So the story drift and all of that is going to be according to CBC and ASCE. Now, we're doing here strength design. What does it mean by strength design? It means that you're going to be determining the seismic forces on the structural members. We're going to have a moment frame. You're going to apply the seismic forces as calculated based on the code equations. And then once you find all of these forces, you're going to be doing the load combinations. And this load combination is going to be according to CBC and ASCE. And this seismic forces here, this is what you call here EH, which means the seismic forces based on the V, the phase shear that you used there. In certain sections, you need to apply the overstrength factor. And this overstrength means that you're going to be taking EH multiplied by omega sub zero. Are you guys familiar with omega sub zero? Have you seen him before? Yes? No?
Yes, in table 12
yes.
to 1.
Yeah, in table 12 to 1. No, here
That's
we
right.
go.
Yeah.
Okay, here it is. So if you're talking about this omega naught, if I'm going to be talking about this moon frame system, this is going to be the box that I'd like to concentrate on. So this one here is going to be the response modification factor, or ductility factor if you like. It's like indication of the ductility, and then you have this overstrength. So what is this overstrength? Certain members and certain, I'm going to say, connections of the structure, you will need to design it for the force, reduced force, based on this R factor of 8. But when it comes to this specific connection or a specific member, you need to multiply this force by 3. So the force that you're going to be determining based on this 8, R factor of 8, we're going to be calling EH. So this is going to be here EH, just EH. So let me type it here. So I'm going to say this is going to be here EH. So EH or E sub H based on V, which is a phase shear, right? That you're going to be doing from the analysis, and of course including R. E sub MH, which is this one here. You see this EMH is going to be equal to EH, which means the forces multiplied by, I'm going to say here omega naught. So I'm going to say W sub 0, like omega naught, if you like. This is the symbol that I'm going to be using. So this omega naught is going to be this guy here. This omega naught. Okay. So where's this omega naught? Where would you get it from? I'm going to say from this table 12 to 1. And this EMH is going to be based on the design forces. So first you're going to be taking the design forces. Where would you get design forces? I'm going to say it's going to be based on this analysis. Like this equation here. like all the equations that we use, right, for CS and all the nice stuff that we worked on. So after you do the CS, you can say it's gonna be based on this, right? We're gonna be doing the CS, right? And then after that you have the V factor, and then which is this V, the base shear. We're gonna be taking it, distributed among all the lateral force elements, and then after that take this force, apply it to the moment frame, right? And of course, gonna be using a factor of R. And for that, we're gonna call, let's say that you have an axial load. For the axial load, you can call it E sub H. For the moment, you can call it E sub H. For the, let's say, shear, you may call it also E sub H, because it's gonna be the force in any structure member, whether it's gonna be axial load, or it's gonna be shear force, or it's gonna be moment based on V. I'm gonna call this E sub H. It's gonna be the effect on the member, whether it's gonna be axial force, moment, or shear. If you take the same axial force based on your analysis in the moment frame multiplied by omega naught, and this omega naught, which is the 3 in case of seismic moment frame, you're going to be now at the level of maximum. We call this include overstrength. So what is overstrength? I'm going to say overstrength is going to be this omega naught. We call this here to be overstrength factor. So I'm going to say here's overstrength factor with this omega naught. Overstrength factor multiplied by E sub H, you get here E sub MH, which is the maximum. Also, we have certain load combinations for it. So when you look at the load combinations, you're going to see also E sub MH. You're going to see it there. And you see this is going to be determined based on the overstrength factor omega naught taken from the table. Which table again? I don't want to forget this. The table is called 12:1, which is this overstrength factor. So what is the reason that we do this? What is behind this? I mean, the concept, why are we doing this E sub M? Because now our goal is not just to design a moment frame. Our goal here is to understand why the code would say anything like this. Why this is included in the code? So we can say certain members, I cannot allow them to yield in the building. I don't want them to dissipate energy. So this members is going to be designed for the overtrends E sub MH. Other members is going to be okay to design for EH. So the member that you're going to be designing it for EH, these are going to be members that you want them to dissipate the energy during the earthquake. The other members, you'd like them to be the elastic range. So during the earthquake, these members designed for just EH, they're going to be going into the inelastic range or the elastic performance, and they're going to be dissipating energy. Those members designed for EMH, you don't want them to dissipate energy. So you don't want them to yield at all. You'd like them to stay in the elastic range. This is the reason. Now we'll figure out which elements later on. Now, the required strength means the demand, right? Like for example, we say P sub U, we say M sub U, we say any force, right? Ultimate is gonna be sub U, this is gonna be the design or required strength. Available strength is gonna be like Phi-MN, Phi-PN, and Phi-VN. So we're gonna call this gonna be the available strength is gonna be Phi-RN. So this R, right? It could be for this R, it could be M or P or V. We call this what? So I'm gonna call this R. Right? Why? Because this is gonna be the strength. Like for example, when it comes to available strength of a welded connection, I can call it also Phi-RN. It's gonna be the strength of that connection. Or it's gonna be like in shear for bolts. I can also call it Phi-RN for the shear for the bolt, let's say group. So this R here, it means M or P or V, depends on the force that you're designing here for. And if you are doing here LRFD, like strength design, right, you're going to be using a phi factor. And phi factor most likely is going to be either 0.9 or it's going to be equal to 0.6. If you are doing ASD, which we're not doing ASD here in this course, but to know how it works, you need to find out instead of Phi-RN, just take this R sub n divided by omega. This omega is a safety factor. This is completely different from this omega sub 0. So this omega sub 0, again, is overtrends factor. I can write it here. I'm going to say it's going to be overtrends. In many cases, you're going to see, of course, English-wise it doesn't work, but it's written as one word here. Just give it overtrends factor, omega sub 0. Just keep this in mind, which is completely different from this omega. Why? Because this omega means is going to be the safety factor that you use when you do ASD design. All right. So I understand now the available strength. Okay. How about this required strength here? The demand. Where'd you get the demand from? I'm gonna say demand, it depends on the member that you design for. And I guess we just covered the demand right here when I was talking about EH and E sub MH. I said that certain members need to be designed for EH. It's giving the members that I'm gonna allow them to go into the inelastic range and dissipate energy. Other members I need to design for EMH because I don't want them to go into the inelastic performance and just to stay elastic. So if I'm saying it's gonna be designed to support EH, it means it's gonna be now the demand. Now, which members are designed for EH, which members are designed for EMH, you're gonna find them in these chapters. So in these chapters here, like DEF and GNH, let me take you here, which means all of these chapters for the member design, you're gonna see exactly in the moment frame which sections is gonna be, or members is gonna be designed for EH and which members that you need to design for EMH. This is why here it says, it refers you back to the chapters. Now, I'd like to look here at the system type. How many systems we have? We're gonna say, okay, seismic force resisting system, SFRS, is gonna be what? It can be what? I'm gonna take you back here. According to this code, you may have a moment frame system. It can be special, it can be intermediate, it can be ordinary. You can have also brace frame and shear wall. You can have composite moment frame system. We're not gonna be covering this. And also you have this composite brace frame and shear wall systems. So this is gonna be all the systems identified by the 34116 or 5 or 10, right? What I care about is gonna be only these two systems. And it's gonna be great if we can cover this 100% and maybe partial of the brace system, or I'm gonna say here, this includes the eccentric and the concentric. So it's gonna be great if we can cover this 100% and a little bit of this. Okay, here's the system type. I'm going to B4. So B3, which means it's gonna be chapter B, item number 3, right? And B4 is gonna be the system type. All right, now let's move here to chapter A, which is general requirements. I'm gonna take you back every time to this chart, if you like, or this slide here, because it includes all the chapters included within the 34116. General provisions here, I guess we talked a little bit about the general design requirements. So we're not really working or moving in order of the code, but that was something important that we need to address. And then after that, we're gonna be going here to general provisions. General provisions, it says, now your structure members is gonna be going into inelastic performance. And we understand that when we say here, F sub Y is gonna be equal to 50 KSI, I'm gonna write it here. When I say F sub Y equals to 50 KSI, is this a test value? I'd like to hear from you guys. When I say F sub Y is equal to, I'm gonna say ASTM, let's say, which one would you like to use here? I'm gonna say 572. This is the one that we'd like to use, 572 or 992. Which one is this 50 KSI? Is this the specified or the test value?
Is a test value.
Test value?
Oh, I think that like is like yield strength.
We call this specified, right? So what does it mean by specified? What does it mean of specified? What does it mean for you in simple English?
It means that this is the value that we were given for ASTM A572.
Okay, which means if you go back here to this ASTM requirements, you're going to see that this is going to be the minimum value that you should expect in the steel section, right? So for example, if the steel that you have there, if you take a sample and test it, give you a yield difference lower than 50 KSI, you're going to say this is not good because in the SCM it says this is going to be F sub Y minimum. So you're going to say specified, right? Meaning minimum value, right? So this is not the test value. So this is going to be the specified value. This is what you're going to ask for. This is what you ask for. But the reality, usually, the test value is going to be slightly higher than 50 KSI. Could be maybe 51, 52, right? It could be 53, it could be 54, it could be 55. It's going to be somewhere there. So the test value usually is going to be higher than this value because if the test value is lower than 50 KSI, you cannot use this structure member and call it A572 in this project. You're going to say, I cannot use it. This piece of steel or this member is not good, or this section is not good. I cannot accept it from the contractor. So your minimum test value is going to be 50 KSI, which is specified. So the test value are expected to be higher than this. So what is the test value for you? You're going to say test value means the actual value, the expected. What should I expect when it comes to the yield strength? So I'm going to say, what is the actual value? The actual value, I'm sure it's going to be more than 50 KSI. Don't you guys agree? Expected is going to be higher than 50 KSI, right?
Yes.
Okay. So if it's going to be more than 50 KSI, I get to be careful. Because when I did my analysis and I found out Feynman that I was working on, and I was trying to find out this curve, right? I'm gonna put it here in a second, right? Gonna take you back here to the previous slide set. I'm gonna say to number 9, right? In this page 11, right? Look at this. Where'd you get this from? This force is not just force, it can be also moment versus rotation, right? So here it is lateral force versus displacement. Also, I can have it as moment versus rotation, or versus curvature, if you like. So I'm going to say in this case, the estimated force, lateral force, and the estimated moment for yield point is going to be higher than that pays on this 50 KSI, because the actual value now is going to be maybe 53. So you got to be careful, because in your analysis here, right, you assumed that the system is going to be yielding at this value, is going to be yielding here, but reality is going to be yielding in a higher value. It's going to be doing this. If I may draw here a line, I'm going to say the actual performance curve is going to be something like this. Do you guys agree? It's going to be doing this. So this is going to be the original, the design one, but in reality, it's going to be doing this. And the reason is because the test value, or the actual value for the yield, is going to be greater than 50 KSI. So now we're going to be in trouble, right? Because we need to know exactly where it's going to be at when it comes to the expected. So it says here, the expected yield stress is going to be equal to some factor. So this factor is called R. This factor multiplied by F sub Y. So, and also when it comes to the ultimate, is going to be R sub T times F sub U. So this factor is going to be called R, right? This R factor that you're going to be using when it comes to the yield strength, we need to magnify it a little bit for the expected value. And for the ultimate, also we need to magnify it a little bit. Because now when we're doing our analysis, we need to be careful, because the steel is going to be stronger than what we think it is. And this is going to create here an issue, because the R factor that we assume in our analysis, if you remember the R factor, what does it mean by R factor? It means this mu. So we can say this is the same as R factor. So I'm going to put here a note, give it ductility, right? The same as the ductility factor, which is same as R. I'm going to put it here, right? What is this R? R in the table that you use. So when you calculate out the design force, you base it on our R factor of, let's say, 8, and yield strength of F sub Y, which is 50 KSI. Reality, F sub Y is going to be slightly higher. And what is R factor? R factor equal to delta ultimate divided by the yield point. And guess what happened to the yield point? It went up a little bit like this. So what happened here to our actual R factor, the ductility factor? It went down because the yield point has moved to the right. When you take this delta U divided by the new delta Y, which is at this red line, it means that your R factor, right, the actual R factor, the ductility factor that you have in this structure, is going to be lower than what you think. So you need to account for this somehow. So the code here says you're going to have this magnification factor, R sub Y and R sub T. And they say in this table, A31, right, they say it's going to be based on the steel that you use. The steel that I'd like to use here is going to be this one. You know, it's going to be the 992, right? This is the one that you're going to see in the code. This is going to be the one available nowadays. And also this one here, 572 is going to be one of these two. In each one of them, I have this R sub Y and R sub T factor of 1.1, which is very good, right? So the increase is going to be 10%, meaning if the yield difference is going to be 50 KSI, the expected is going to be equal to 55 KSI. I'm saying now the expected yield f sub y expected is going to be equal to how much now? It's going to be 55K. So am I clear on where did they get this 55 from? The expected? Yeah, so the expected, let me put here a point. I don't want to put dash. No one would say that I'm going to be subtracting any value. I just take this 50 here, multiply by 1.1. And also for the ultimate, if we say the ultimate is going to be 65, we just simply multiply by 1.1, this factor. But look at different steels. If someone's going to say here, let me use the 529, grade 50. If the contractor now wants to change it for you, you start construction, right? And your original design, you call for this steel. And then the contractor said this is going to be grade 50. All of a sudden now he wants to change it to 592, 529, grade 50. You're going to say this is not a simple change because all my calculations were based on R sub y and R sub t of 1.1. Then we changed to 1.2. I'm expecting now higher yield strength and higher ultimate strength. So my analysis is going to be completely different. So we need to understand that the expected value here, again, is going to be based on the steel, I'm going to say your designation that you plan to use in your project. Again, most likely would like to use both of these two. This could be our target. I'm going to say, how about if I'd like to do a moon frame to maybe some steel tubes like HSS? I'm going to say, okay, look at this. This is going to be the most likely one to use, right? For steel, for HSS, as it says here, HSS, I'm going to say most likely it's going to be this guy here. Look at the factor, 1.3, 1.4. Big difference, right, in your analysis. So you cannot just switch between the steels that easily. You need to understand the effect, how this is going to be affecting you. How about any other sections like A36? Look at this. Big factors, right? How about this? If you like to go here to 572, just for the plates, look at the factors. So you have different factors for different steel. I'm going to say your designation, if you like, for ASTM designation. So, okay, very good. How about the bolted connection? What type of bolted connection am I allowed to use here? Yes, when it comes to bolted connection, I guess I need to be careful about the type of bolts, and the one that I'm going to be using is going to be the slip critical. You remember, guys, the slip critical, we discussed it, went through it quick. We say it's going to be high trans bolts, right? It has to be high trans bolts. It's going to be pre-tension, slip critical. It's going to be important. Slip critical, the resistance is going to be based on the shear between the bolt and between the plate. So when you have a bolt between a plate and instruction member, or between two plates, your design values going to be based on the slip critical values, right? Why? Because it's going to be pre-tension. Pre-tension means that you're going to be tightening it to a certain limit to say now it's going to be pre-tension. So the trends here is not going to be based on the bearing like the table we have used. Are you guys familiar with what I'm talking about, or not really? You forgot it.
No, I think we know this.
Okay, thank you. So this available shear, this is going to be based on bearing. And the only allowed, I'm going to say here, bolts or threaded parts to be used is going to be this A and B. How about C? Can I use C? I'm going to say yes. But can I use this A307? I'm going to say no, because this is not high trans bolts. This groups is going to be high trans bolts, and this one is going to be machine bolts or conventional bolts, if you like to call it this way. So the A307 cannot be used inside of moon frame or shear walls or eccentric brace frames or brace frames. You cannot use it there. It has to be high trends. So this is going to be an important thing. High trends, it's going to be pre-tension, slip critical values. How about the welded connection? I said welded connection, there is no problem. It's going to be the AWS D1.1, the code there that we discussed earlier. And there is no tricks here for you. It's going to be just the AWS, the welded connection that we have discussed. But when you look here, there's going to be a big difference in the bolted connection. As far as for the weld, there's no big difference. We have the V-notch. This give you like a test that we're going to be doing and give you here some test values. Give me a second, please. All right. So next to that, we need to talk about this protected zone, which is very critical here. And also this protected zone is going to be a very good question, if you like. Very good potential question. It says here, protected zone in the SMERF, in the size point resistant frame, is going to be where? It says here, at the plastic hinge region. From the column face to the end of the cut. What cut? I'm going to put this here. And say, let me put here the previous slide set, the old one. I'd like to see what cut and what is you're talking about. Here's a mount frame. And this is going to be the area that we call here protected zone. You see in the protected zone, it says no welded attachments or holes, including shear studs, which means nothing that you can do here. And this gives you the end of the cut. Look where the cut is going to be at now in the RBS. Here's in the RBS. So I'm going to say here's the protected zone, which is this section here of the mount frame, right? We don't want you to do anything here. Why it's protected? Because this region here is going to be exposed to a lot of strains. The strains here is going to be high because this piece of the mount frame is going to be going to the inelastic range, and once it goes into the inelastic range, you don't want any welded connection to be here. Otherwise, it's going to be reducing the ductility of the system. It's going to get damaged totally. So look at what happened here. This section here of the mount frame, you cannot attach or weld anything to it. It's going to start from the face of the beam to some place here that we need to also have to calculate it. Now this can be called.
Professor?
Yes.
Don't we have modes over here that joins the shear tab to the beam section?
The shear tab?
Yes, sir.
It's okay for this shear tab for this connection. The problem
But
usually
it
is going
has
to be
modes
in
due
the
to
problem.
which we have holes.
Yes, the problem usually is giving the flanges. So the problem here that we have is giving the flange. So this issue of protected zone, if I'm going to go back here, is going to be in this section here, that you don't want to attach anything to the top flange and you don't want to attach anything to the bottom flange. But
so the protected zone is for the flange of the section?
Yeah, it's going to be the flange of the section, but also it is not recommended that you're going to be welding anything in here, right? You don't start with, let's say that you have a duct hanger, for example, don't try to weld it here. Stay away from this section. Only the shear tab is going to be okay to attach it to this beam web, if you like. Okay.
But sir, we do have a cut on the flange of the beam in the protected zone.
Actually, you know why this cut? You know why we're doing this cut? Because when I
Yes,
do,
sir.
yeah. So it is protected, which means don't weld anything. It does mean don't cut it this way. We really have to cut it this way. Otherwise, we don't have a space to this or a place to dissipate the energy, and the space of the energy is going to happen right at the welded connection, which is not good.
But sir, when we have two plates, like, can
Cover
you go?
plate? Yes.
Yes, sir.
Yes.
So, sir, in this case, don't we weld the plate or don't we mold the plate to the flange?
No, this is fine. With the cover plate, this is going to be the only thing that you can weld, but you don't attach a deck, a metal deck. You don't attach this studs. You don't attach any exterior pieces. So the
anything
effect,
that's not required to attach the
yes,
section and the column, that's not allowed in the protected zone,
this is
right?
correct. This is correct. But this cover plate is needed because it works very similar to the cut. It pushes the plastic hinge from this location to that location, right?
Okay.
It is controlling the location. So I'm going to say, here's the first one. It's going to be the plastic hinge from the column face to the end of the cut. I said, okay. How about in the EBF? This is the shear link. So in the EBF, you can see the shear link. Let me go to it. Here's the shear link, and it says in this location here, do not weld anything, and look at the detail. You have here studs, but nothing here. So I was going to say, how about this stiffener plates? You see the stiffener plates, the vertical ones? You say, yes, we need them. This is going to be the only thing that you can weld, but don't weld anything from the bottom not related to this EBF. Don't weld anything from the top. Just leave it free, because it's going to be this piece here. It's going to be going the shear yielding. It's going to be dissipating the energy. So I don't want any attachments here to it. Okay. This is going to be the EBF. How about the CBF, concentric brace frame? It says here the middle 1/4 of the brace. I'm trying to understand what is the middle 1/4 of the brace. So I'm going to zoom out here. I'm going to be going to this concentric brace frame, like this one, for example. I'm going to say the middle quarter of the plate. I'm going to be taking the plate, I'm gonna say start from here. Let's say the middle quarter, start from here, all the way to here, right? This is gonna be the section of the brace frame, or the brace is gonna be exposed to, you can say, yielding and buckling compression, and this is how it's gonna be dissipating the energy. And also this section is gonna be going through the inelastic response or behavior. So if this is the case, you don't want to attach anything else to it, which is very critical here. So usually we don't allow anyone to weld anything here in the middle half, if you like. It says here in the middle quarter of the brace, but as usually in our business, we say, now where's the brace? Because this is not really clear in the code. Now where's the brace? Is the brace from here to there, or the brace from here to there? Where is one brace? So I guess in this case, you're gonna say, well, this is gonna be a brace, another brace. Someone else is gonna say, this is gonna be one brace. Just to be in the safe side, keep this half to be out of any welding and any requirements. About if it's gonna be here, I'm gonna say here, now this is clear. This is gonna be one brace, this is gonna be only 1/4, right? This is gonna be here, I'm gonna be taking only 1/4, right? Only 1/4. So it's gonna be much smaller. Okay. So now I understand the protected zone and I understand why it is protected. Now, can someone explain to me why it is protected? What is the reason that you call it protected and it is protected in our design?
Controlling the ductility of the structural system.
Does it control ductility?
To ensuring the ductility that we choose
Okay.
it for the R value.
Okay. Because this is going to be the places
it
at
is
which you're going to be
called-
dissipating energy. This is going to be the location that you're trying to dissipate the energy. You're going to allow these sections to go into the inelastic behavior and response. So this is why you'd like to protect them. You don't want to weld anything else to it. Otherwise, you're going to be reducing ductility of the system. Yes, Maheen, go ahead. You have a
No,
comment.
I was just explaining the same thing.
All right, thank you. Thank you. Said okay. Chapter D. What's chapter D about? You guys remember what chapter D about? Let me go back quick, but it's gonna be about this mirror. Size movement resisting system. I'm gonna say here chapter D. I'm gonna go back to here. It says general requirements for member and connection design. Requirements. So what's chapter D about? Let's see what is really important there. What's gonna be the member requirements and how about the connections? So okay. Guess I'm gonna stop here. Now I'm gonna be moving to the next slide set. Any questions here? Yes.
No, no
Right.
questions in the moment.
Yeah, we start here with the special moment frame. Now we need to understand what happened there and the location of the plastic hinge and how can we do our design. I guess we have discussed this before in the pre-Northridge moment frame connections. What happened during the earthquake and after the earthquake? People go out like engineers. You go out to inspect and observe what happened during the earthquake to some damaged buildings. And this is what they have found. They really found lots of fractures in the welded connections here. That was a kind of something new that they didn't see before. So during this Northridge, when you see here lots of failure, now we need to learn from the earthquake. So what's the lesson here? The lesson is we have some issue because this building material is very brittle, causes here failure during the earthquake. So we cannot allow it anymore. This is why we start to think about coming up with, you can see here, coming up with this connection with the RBS or with the cover plate. So what we're going to be studying here when it comes to analysis is going to be this reduced beam section. We call it RBS reduced beam section. This is going to be the one that we'd like to use. So what happened? Look at some testing here for a connection. And the connection is going to be the pre-Northridge connection. As you see here, you have a vertical member, which is a column. Here's give you the column. We attach to a strong wall to something very strong, but this give you the column that you are testing. And this give you the beam, right? And this give you like a setup in the lab. Here's something strong, right? There's like the rig or the strong wall that you are attaching this to it. This give you the column, right? Because you'd like to simulate the existing moment frame system. It's gonna be your beam, and then you're gonna start to apply here some forces this way. As you see here, it says the force is gonna be plus or minus, meaning at one time it's gonna be like this, the other time it's gonna be up and down. So plus or minus doesn't mean it's gonna be negative force or positive force. It actually just means the direction. We're gonna be putting this up and putting it down, right? At the beginning, it's gonna be in the yield, right? In the yield performance, and at certain point, it's gonna be going to the inelastic performance. We call this hysteretic behavior or hysteresis curve, if you like, for the testing. And on the x-axis, as it says here, you're going to have the displacement. So displacement here is going to be in the x-axis. And the y-axis, you're going to be looking at the force. So what displacement? I'm going to say this displacement from this point when it goes up and goes down, right? So it's going to be to the right side. It means it's going to be going up. And where's up? It depends on your definition. For us, we don't really care because someone can call when you pull it up, it's going to be positive. When you push it down, it's going to be negative. Someone is going to be looking at this differently and saying, no, when you go up, it's going to be negative. When you go down, it's going to be positive. So it's not really a critical issue for us because all what it's doing here, just taking this loops and put it in this side or this quadrant and taking all of these loops and put it there. But it's not really critical for us. So at the beginning, you start from this point and then you start to apply some load. And let's say this load is going to be going up. So what happened? The positive direction here is going to be up. And also the positive direction of displacement also is going to be up. So you're going to be moving this way from the yield point, you're going to be going up. And then after that, you're going to be stopping the equipment, like the hydraulic ram, which is the actuator that you apply here the force with. Now we're going to start to push it down. Now we start to push it down, it's going to be going down here. It's going to be start to yield at this point, and then you're going to be going back and forth till you have failure. Now, once you have the failure here, what happened? You have here break, right, in the welding connection because this welding connection is not good enough. So now the system stopped. So what is the use of this? You're going to say, well, this is going to be very important for us because the area here contained by one loop is going to be equal to the energy that you dissipated. So this area here, we say area contained by this hysteretic response, and say area contained is going to be indicates the amount of energy dissipated. I'm going to say energy loss. So during the earthquake, right, this area here indicates again the energy dissipated or energy loss. And you'd like to have bigger area here as much as you can. Because if you just imagine that you have linear performance, which is the system is going to be going up and down like this, just through this line here, this line path. So what's going to happen? It means you don't have here energy dissipation at all. And the entire energy is going to be converted into damage into the building and the formation, which is not good. So once you have here some area contained, it means your structure here is dissipating energy in the right way that you want it to. Also look at the yield point. I'm guessing yield point is almost here, right? This one starts to come down, maybe here, somewhere in this location here. And this is gonna be the ultimate, this is gonna be the yield displacement, and this is gonna be the ultimate displacement. And as you see here, you don't have lots of ductility. So what's ductility? Ductility is gonna be equal to ultimate displacement divided by yield displacement. So someone's gonna say, if you really give it enough attention, maybe the yield start at this point. So look at this. So I'm gonna say maybe about 3/4 of an inch for the yield displacement and maximum displacement 1.75. Your actual ductility factor now is equal to 1.75 divided by 3/4 of an inch. So okay, good to understand what is this about and the performance curve that we are getting out of it. Now look at this here. What happened? Now we have this RBS. Now look at this. This is going to be here the pre-north ridge, the cyclic test. Number 5, that was just this number at 1.5 inch. So what is the 1.5 inch? 1.5 inch is going to be the maximum displacement that you like to go to, but usually the system would push you a little bit further away from it. Look at this one here. The same connection is going to be test number 1. You'd like to push it here to 1.9 inch. So we say, yeah, 1.9 inch You're talking about this displacement here. Look at the beginning again. You start by pushing it. Yield point start maybe about here, and I was able to get all the way to this number here, coming back, and this area here represents the amount of energy dissipation or energy loss. Now, with this kind of poor performance, if you like, because if you remember the R factor, what was the R factor for a moment frame? Anyone remembers? Ductility factor?
Special moment frame,
Is it
8.
8. Now, I
For a
want to
special
hear,
moment frame.
yeah, for a special moment frame, this is going to be the one that you like to use. But when you look at this one, look at the yield point. Compare this yield displacement with this ultimate displacement. How much is this factor here? Can you say maybe 2?
2.3.
Right? Maybe 3? Yeah, from here to there, divide by this. Maybe 2, maybe 3, that's it. Now, this is a reason that you'd like to have this special moment frame. How can we make it special? By providing this RBS connection. So the reason that we have it, this the connection to RBS is to make it special, increase the ductility for it. The thing is, how would you build it? What is the best practice if you like to build it? Just say, when it comes to the top flange, it's gonna be full pen. We call this full pen, which means complete penetration well. Come to the shear, it's gonna be a shear tab, and then after that we have the cut. What is really needed from the SMER, from the size moment frame, the special one? It means when you are at rotation of 4% radians, so someone's gonna say, what does mean by rotation 4% radians? I'm gonna say, just imagine this is gonna be your moment frame, right? This is gonna be here your moment frame. Maybe I can draw it here. And this moment frame is gonna be exposed to some rotation. Let's see, what does mean by rotation? Rotation meaning this way, right? This column is gonna be common in this location here. And also this column is gonna be like this. And this beam is gonna be also like this, right? It's gonna be something like this. So this is gonna be the moment frame, the new shifted or the new location of the moment frame. So I was gonna say, how much is this angle? See this angle between the first column location and the final column location? We call this what? Let me put here a name for it. I'm gonna say angle rotation. This angle rotation, someone can measure it. And if you like to measure it, there's more than one way. This angle is very small. So I'm gonna say the angle is gonna be equal to tangent of this angle. Tangent of this angle is gonna be 10 off. Now, is this in degrees, this angle? I'm gonna say no, it's gonna be angle in radians. So I'm gonna put here a quick note here. I'm gonna say this gonna be the angle in radius. So this angle in radius, you'd like it to be about 4%, which means the slope of this line. So the slope of this line here is gonna be roughly 4%. Means that the angle itself is gonna be also 0.04 radians, right? At this 4%, you'd like to have enough strength in the system to be 80% of the maximum force that it can go to. So if I'm gonna take you back here to this hysteretic response, you're gonna say, look at this. The system here didn't come down. I'd like to see something like this. I'd like to see something like this. I'm gonna say, let me use this line here, this P line. Let's give it like this here, 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 and then I want it to come back down a little bit, and then come back. This is what I'd like to see. And this is actually what's gonna happen. So we'd like to see here a drop. And once this drop is gonna be reaching to be 80% of the maximum force it was allowed to go to, I'm gonna say now the beam is good at 4% rotation. So, but the problem is gonna happen when this point is gonna be coming down like this, which means that the residual force is gonna be less than 80% of the maximum M sub P, or maximum force that's gonna be able to at 4% rotation. So someone's gonna say, now how can I figure out this rotation? I'm gonna say, if you are able to find out this amount of displacement from here to there, right? From here to this point. Why this point? Because give you the point that we're talking about. Take this displacement as in inches, divide by the column height. And of course, you need to convert the column height into inches. So in this case, you're going to have the slope of this line. Let me go now forward to it. The slope of this line is going to be equal to the horizontal displacement divided by the column height. At this point here, when you're reaching 4% for the rotation, we'd like to see 80% of residual moment or force. We don't want this to drop a lot. If you have a moment frame that can do this for you, and you do any other design, which means that you do RBS, you do any other invention that you'd like to come up with, you should be fine. So the code requirement here, at 4% rotation or radians, you're going to have 80% of MP is going to be still there, which means the moment frame did not collapse yet. You still have 80%. When you're 80%, it means that you're going to be in the inelastic range, but you're not really collapsing the moment frame. We have here two ways of doing it. The very original one, when the code was written, it was based on the reduced beam section, the RBS. And then after that, they came up with this slotted web moment connection. It's kind of newer than this, but everybody likes to use this one. It's just easier. There's a company that likes to do this. To this company here, they do design build. What is design build? Design build means that they do the design and then they build themselves. You cannot really do it on your own. You cannot just put in the drawings and give it to any contractor to build it, or any fabricator. The steel fabricators give you only this company for the SSDA. I'm gonna show it to you here for quick, and then we can continue. Here's the SSDA. You see what they're doing here? They are cutting the web. You see this way? They first put a pilot hole and then they slot it this way. So we call this slotted web moment connection. It has a pattern. This is why you cannot really use it and you need to give it to them to build it for you. Now compare it with this guy here, with this RBS. Someone's gonna say, well, I prefer the RBS because anyone can just build it for me. Do you guys see anything bad here in this picture about this RBS?
The connection to the web.
Yeah, you're not supposed to do any attachment to this section of the beam. And look at this. You have this angle to support the metal deck, and you have another piece that comes this way, and they simply weld it here and weld it here. That was really bad. We call this unauthorized attachment. You're not supposed to do it this way. If they'd like to do anything like this, what do you need to do? Just so you guys know, you see this angle? They can put maybe a stronger angle, weld it here. This will be the last point to weld it at. Not weld here, not weld here, and just extend this angle right here and weld to the column. This angle needs to be extended, weld to the column, and this gives you support on the metal deck. So this kind of connection is not good. We don't like it, not authorized, and this gives you reducing the ductility of the moment frame. Okay, so here's the reduced beam section, and the second one is giving the slotted web. Again, I'm not going to be covering it, but you need to know about it, and you need to know that if you like to do it, it's going to be fine, but it's going to be only one fabricator to do it for you, so that you control the cost of it. We have some improvements here in the RBS. I'm going to show you the final thing, the final design, which we have it in our details, the details I showed you. So that was a basic one, right? The reduced beam section. You're going to have here full pin weld. You're going to have continuity plate. So this one here we call continuity plate. So this will be here the RBS. And the RBS means from here to here, top and bottom flange. Right? Let's give you this and this. We're going to have here a shear tab. So we're going to call this to be shear tab or plate. We call this continuity plate. We're going to have 4 of these. One here, one the other side, one the bottom, one the other side. We call it continuity plate because this actually represents continuity to this flange, right? We have also another thing that we call Doppler plate. This Doppler plate is going to be a plate that we add next to the web. So you usually put it from one side. It's going to be either this side or the other side to make this web kind of thicker. So in some cases, we have some trouble with this column web and we need to make it stronger. So we bring a plate and attach it here between these 2 continuity plates. Let me show it to you. Now here's the beam, shear tab, the RBS connection. give me protected zone. In plan view, here's the RBS, the cut, the plate at the bottom, some bolts. This top here is going to be full pen. See this? It says typical CP, complete penetration continuity, right? It's the same thing. So you see the symbol for it. It's going to be like this black triangle. So this needs to be done this way. And then also look at the web. The way that we cut the web of the beam, see this? You really need to do it this way because we call this pre-qualified connection. You are just following one of this connection, the code. So you really need to do it this way. And this here to reduce all the fracture and all the increase in the stresses, right, at this connection here. This plate here is a backing plate. We just a plate that we put it there. And by the time you finish the weld, you need to knock it down and then grind this area here. And now we're done with the beam itself. Here's the column. We're gonna have this continuity plate. We're gonna have top plate. There's gonna be one plate on each side, as it says here, continuity plate. Each side of the column, top and bottom. We're gonna have both of these two plates. And also we need to weld it. It's gonna be also complete penetration. So what's gonna happen when you have a force coming this way as in tension, it needs to be transferred. So let me put it here in the plan view as if I have tension force. And the tension force, of course, it's not gonna be coming at just one point load. It's gonna be coming here, one part here, right? Through the flange of the beam, and one part is gonna be coming there. So you don't want this flange to get bent. Otherwise, you're bending this flange and you're making it this way, right? You don't want this to happen. So what happens, you provide this continuity plate so that the tension force is gonna be coming through the continuity plate like this. And then eventually transfers to the column web. So this is the reason that we have this continuity plate. Transfer whether that you have tension force or compression force on the bottom flange. And of course, you know that you are talking about seismic. So whatever that you call here tension, in a second is going to be compression. So this force direction is going to be changing. It's going to be fluctuation from side to side. This is what you call here the Doppler plate. Here's Doppler plate is going to be this big plate, right? So it's kind of you're doubling the plate of the beam web of the column web. You just put here another plate, and then you weld it with the primitive. The reason that you do this, if you find out that still with this continuity plate, you have some trouble with the amount of forces that you go there, right? And if you feel that the plate thickness is not strong enough, you start to add another plate and weld it to it. So make this connection, we call this gonna be the beam column connection, you make it stronger. Okay? Any questions? No questions? Okay, good. Look at the test for an RBS. Look what happened. I was just talking about the volume here for the area, right? Contained by this hysteretic behavior. Look what happened. Where's the yield point? You can see yield point. Look here at this line. Look at this line here. Let's give you the elastic. And look what happened after this. It is almost yielding here, right? And where's the ultimate? I'm gonna say now it goes like this. And then it drops down a little bit. So what's important, I'm gonna say that I'm gonna have here enough strength compared to this strength is gonna be more than 80% of it at 4%. Look at the ultimate displacement. The ultimate displacement is gonna be here. What ductility factor do you have in there? Let's say the ductility factor is gonna be really big, right? You're talking about really big ductility factor because they're gonna be taking this. Let's say if this gonna be displacement, you take this displacement divided by the amount of displacement here. Now this chart that you're looking at, it's not really lateral force versus displacement. It's gonna be between bending moment versus, look at this, it's gonna be rotation. So I said, now I understand rotation. Rotation is gonna be the slope of the column line, if you like. And look what happened to it. This is gonna be at 4%. So this is gonna be the 4% we're talking about. And at 4%, the question is, did we drop to about 80%? I'm gonna say no. The system is still strong. So this is actually, the performance is great. Look at this. It has a great performance, if you like, right? And look at the amount, this volume here, for this area here included by this hysteretic loop. It's really big. Compare it, if you like, just to do here a comparison. So what you usually do, you need to look at the area contained for some given lateral force and displacement, or moment and rotation. Look at the way it looks here. It is not really pinched. You have nice big loops, but look at this one here. It's kind of pinched, right? So this is not good. The ductility of this system is not good, and the amount of energy that you dissipate here is not really good. Look at this one here. It's almost like a line, but look at this one, and the ductility factor is like 2. Now look at the ductility factor here. Our ductility factor is easily, you're talking about 10. Look at this value here, right? Or maybe this value here. Call this to be the yield point. Look at this value compared to this value. I'm gonna say maybe 10. So actually, when you consider a ductility factor of 8 for this special mold frame, it's not a bad idea, right? So actually, our factor of 8 is kind of, I'm gonna say, your conservative value, because you have a good ductility factor up to 10 easily, according to this test values that we're looking at. Any questions?
When would you choose which one to be the yield and the ultimate? Do you just go for the center one and then follow it through until it makes its curve?
Well, when it comes to definition of the yield point is not a sharp point. So I don't want you to expect that that you're gonna have here a straight line, and then after that you're gonna have another line. This is when it comes to analysis, right? So in this
Right.
case, I'm gonna say here's the yield point. But when you do actual testing, look what happened here.
It all
Look at
curves.
this. It's all curved. So what you usually do, like if you have a curve like this, usually the way that we do it after we get the test results, we do a kind of, if you like to call this a tangent, and then we do another tangent, right? And when these 2 points or these 2 lines gonna meet, we're gonna be taking a line like this and say, okay, this is gonna be our yield point.
Okay.
And our actual point is gonna be right here. It's gonna be this point here. Interaction or intersection between this curve and between our vertical line. And this vertical line is gonna be based on this. So actually you can do something like this if you like. And then if you like to go more detailed, don't forget that the quality of the background is not really high. So someone can do this. It's gonna do a tangent here, and this is gonna be the first tangent, and then we meet. You're gonna say now this is gonna be the yield point, just to be exact,
Okay.
right?
Right.
So this is gonna be based on testing. Based on analysis, it's gonna be very simple. We're gonna say this is gonna be the point. Reality is you're gonna have a curve here, right? So you do a tangent when they meet, you're gonna come here with the vertical line to find out the amount of yield displacement if you want to. Let's give it like this, right? And once it hits the curve, you're gonna see now this give you the point. Let's say that this is here a test, one of the tests, right? One of these values. And let's say that this give you the 0 point, because actually I don't have a clear one here. So I'm gonna say here's the first tangent. You can just take this line. You're gonna fix the slope. You can see here's the first tangent, right? Do you agree? Maybe this kind of a clear picture or a clear section of the picture. Give you the second one. You're gonna say this give you the second one, right? And then once they meet, you're gonna say, okay, this give you the point. And the actual yield point in terms of force and displacement is give you this one here. Give you this one here. So I don't want you to expect during testing that you're gonna have a very clear, definite point. Right?
Okay.
But the ultimate point is easy to identify because it's giving the point at which that you have really to take it down, right? When the force is coming down. So this is gonna be an easy one. This is where you stop. But this one is gonna be tough to define.
Right. Okay.
Also look at this. Yeah. Also look at this. Here, locating the yield point, if I wanna locate it here, I'm gonna say, okay, let's start from here. Let's give you the first tangent. Here's the second tangent. Where do they meet? Let's say they meet right here. And this give you the yield point. This point here. It's gonna give you the top when you come to the force because the force is gonna be right here. And this give you the yield displacement. But the lesson out of this is when you look at the area contained by one loop, right? This give you the amount of energy that you dissipate in one cycle or in one loop. Look at the way it looks here. I mean, it's kind of pinched. The other one is like bulged. Feel that is like if you like to think about this as a balloon, for example, right? And it's gonna be like kind of flat. Look at this one. It's really filled with air, right? Look at this one. So we feel that this is healthy because you dissipate here lots of energy. This gives you like the comparison that you like to do. And actually, if you're doing like a thesis or you're doing like some research, part of what we do after we do some testing, then we start here to look at the area contained by this loop. And we have a software, you can build a software for yourself. You say for each loop, how much was that area? And then you try here to convert this area because this area is going to be based on force and displacement. You understand that the work, you remember the equation for the work done? Yes, anyone remember? Work equals to what? In thermodynamics and mechanics.
Half of stiffness, displacement
Is going to be equal to the force multiplied by the displacement. Right? Any work. Right? Do you know the energy? You remember the potential energy and kinetic energy and this kind of energies? So the potential energy is going to be equal to the weight multiplied by the height based on the location. We have also this work. The work is going to be equal to some force times the distance. So I should be able to find out this area here, and this area would be representative of the work in terms of the force unit and displacement unit. And once I do it here, right, I can have the amount of energy that I dissipated during that week. So I can really compare between two systems by testing them and look at the contained area, if you like. This is a bad picture that I talked about, and they said this is not going to be good because you need to extend it. So I guess I should be able to come in the exam and give you a few pictures and say, find out the bad things in here. Kind of criticize this connection and tell me what's wrong with it. This could be one of the things that maybe I can bring it to you. And maybe also welding some stuff, let's say in the ABF or the concentric brace frame and this type of thing. Now, also in the steel moment frame, you need to provide braces for the bottom flange because the depth flange here is braced by the metal deck. By the bottom flange, it is not. So what we do here, we put a vertical stiffener and we call this a brace. This is different brace from the brace of the moment of the brace frame. This is going to be completely different. It's going to be the moment frame here, and then we need to provide some braces to brace the bottom flange. Otherwise, this bottom flange is going to be going right and left. I guess I'm going to stop at this point here. And you guys have any questions for me? Hello? Anyone
No.
here?
No, I think we're good.
Okay. Anyone needs
Not ready.
any questions after the lecture? Do you need to have to see me at the office hour today?
Sir, are you gonna show us our papers in the office hour today?
What paper?
Our midterm exam, I mean.
No. The second midterm?
Yes, sir.
No, I didn't grade it yet. It's gonna take some time. There are many people here.
Oh, okay.
All right. Anyways, if you need any help, if you have any questions, we can meet tomorrow also at the office hour.
Professor, are we
Yes.
having class on Wednesday? I saw on the syllabus it's a holiday, and
Yeah, it is a holiday. Yes.
so no class then.
Yes, unless you guys want to.
I think we're good.
Okay. All right, very good. All right. So let me know if you have any questions, come by tomorrow. Okay. All right.
Thank you,
Have a good night.
Professor.
Okay.
Have a good
Thank you.
night.
Good night.